Have you ever stopped to think about this whole unseen world? I mean, the one operating just beneath what we can perceive,
Mm,
where engineers are controlling things at scale so tiny, it's almost, well, unimaginable.
it really is mind-boggling.
So today, we're taking a deep dive right into that frontier. We're going to explore nanopositioning systems.
Excellent topic.
Okay, let's unpack this. Our conversation today, it's really built around a great source. Cognitive Market Research's report on nanopositioning systems, market trends, and future opportunities. It came out February 2025, got an update in June.
Right, a very current look.
Exactly. So our mission here is to get through this pretty quickly but thoroughly figure out what these systems actually are, why they're becoming so incredibly important for cutting-edge tech, and what the future holds for them.
Sounds good. Where should we start?
Well, before we get into the market side, let's just level set. What exactly are we talking about with nanopositioning systems? What gives them this incredible precision?
Okay, so at their core, nano-positioning systems are devices designed for extremely high precision. We're talking about controlling the position of an object right down at the nanometer scale.
Nanometer scale. Remind us how small that actually is.
It's tiny.
Yeah.
A nanometer is a billionth of a meter.
Mm-hmm.
So you're positioning things with effectively atomic level accuracy.
Wow. And how do they do that? What's the mechanism?
Well, what's fascinating is that typically these systems use something called piezoelectric actuators.
Piezoelectric actuators. Okay, that sounds complicated. How do they manage such microscopic movements?
It's actually quite elegant. Piezoelectric materials have this special property. They change their shape in incredibly small, predictable ways when you apply an electrical voltage.
Oh, okay.
So imagine a material that expands or contracts by just maybe a few atoms width. That's how you get movements much, much smaller than a human hair.
Yeah.
That's the key to their sub-nanometer precision.
Right.
And this high degree of accuracy, it isn't just, a nice feature. It's absolutely fundamental for what they do.
Incredible. That level of precision is hard to wrap your head around. So where do we actually see this in action? What sort of real-world applications really depend on it?
Oh, they're foundational in many fields that need that ultra-high precision.
Mm-hmm.
Think advanced microscopy, like atomic force microscopy.
Right, where they sort of feel surfaces at the atomic level.
Exactly, that kind of thing. Also, semiconductor manufacturing, absolutely critical there. And in the whole world of optics and photonics, aligning lasers, lenses, they're also crucial in things like optical coherence tomography, OCT scans, used a lot in eye diagnostics for super detailed imaging inside tissue.
Okay.
So basically, any field that's pushing the boundaries at the smallest scales relies on these. Research labs, healthcare, making your next computer chip. They're everywhere, really.
So clearly fundamental, but what's maybe surprising is how fast the demand for this level of precision is, well, exploding globally. What are the numbers telling us?
Yeah, the market is definitely seeing some remarkable growth. According to that Cognitive Market Research source, the estimate for 2024 was USD 162.5 million.
Okay.
And it's projected to hit USD 463.5 million by 2032.
Wow, that's quite a jump.
It is. It represents a compound annual growth rate, a CRGR of 14.000%. So steady, strong growth.
14% CAGR. That's really impressive. What exactly is fueling that kind of expansion?
Well, a key driver is just the relentless increasing demand for precision across a really diverse range of industries, too.
Which one specifically?
We're talking semiconductor manufacturing, obviously, but also aerospace, defense, advanced medical applications.
Right.
And their use is also growing a lot in cutting-edge nanotechnology research, material sciences, and also in critical semiconductor testing.
It makes sense. And you connect this to those really next-generation technologies too, don't you?
Absolutely. I mean, take quantum computing, for example. The reason it relies so heavily on nanopositioning isn't just about things being small. It's about the need for almost perfect alignment. You need to maintain these incredibly fragile quantum states. Even, a single atom slightly out of place can mess up the whole calculation.
Ah, I see. So the precision isn't just enabling products, it's enabling whole new sciences.
Exactly. That's why this precision is key, not just for new products, but for entirely new sciences and, next generation technologies.
So if we're talking technologies enabling new sciences, what specific trends are popping up right now? What's happening at the cutting edge?
Well, one really prominent trend is the continuous development of advanced technologies that specifically demand that nanometer scale positioning.
Like what? Give me an example.
Think about nanolithography. That's essentially printing circuits onto chips, but incredibly tiny, right? Pushing computing power
Yeah.
limits. Or ultra-precision optics, lenses for next-gen telescopes, or powerful laser systems that need alignment down to the nanometer. And like we mentioned, there's also increasing use in healthcare, particularly advanced imaging. That could mean, more accurate diagnostics, maybe even new therapeutic approaches down the line.
Given all this growth and how critical they are,
Hmm.
where are we seeing the biggest impact geographically? Are certain regions really leading the charge?
Yeah, if you look at the map, so to speak, North America is expected to dominate the market currently,
Why is that?
mostly due to its really strong focus on R&D, research and development, and just being an early adopter of advanced tech.
Makes sense.
Europe is following pretty closely. They have very robust industrial and scientific research applications driving demand there.
Okay.
But the Asia-Pacific region is also coming up fast as a key growth area,
hmm
especially countries like Japan and China. They're investing heavily in advanced manufacturing and research.
So Asia Pacific is one to watch.
Definitely. In
Good.
fact, it's projected to see the highest growth rate. The forecast anticipates a CAGR of around 16% by 2025. That acceleration is really driven by industrialization and just innovation in high-precision technologies.
Right. So the global race for microscopic precision is definitely heating up. What does that mean for the companies actually in this space? Sounds pretty competitive.
Oh, it truly is. The nanopositioning market is highly competitive. You've got several major players really vying for the lead.
Who are the big names?
Well, as of 2024, the data showed Aerotech Inc. holding the largest share, around 17%. Then you have Physik Instrumenta PI, they're often called, with about 12%, and Sidret Technologies around 10%.
Okay, so Aerotech, PI, Cedrat. How do companies like that stay ahead in such a demanding field? Is it just about making the tiniest movement possible?
It's actually a lot more nuanced than just the scale of movement.
Yeah.
They're constantly investing and heavily in R&D, trying to enhance performance capabilities, really focusing on precision, yes, but also speed and durability.
Speed and durability matter too.
Absolutely. And what's also interesting is they're very active in strategic moves,
Mhm.
mergers, acquisitions, partnerships. The goal there is really to expand their product portfolios, maybe get access to new technology, and crucially, reach a broader customer base, especially, in those fast-growing markets like Asia-Pacific.
Right.
But fundamentally, what sets these systems apart is that ability to deliver precision right down to the nanometer scale. That's why they're gaining significant market share over, say, older alternatives, like maybe just standard piezoelectric positioners.
Yeah.
Their resolution, accuracy, and reliability are just superior.
And those qualities are non-negotiable for these advanced applications.
Exactly. Non-negotiable.
Okay, it's clear this tech is indispensable. But, even the most innovative things face hurdles. What are the biggest challenges for this market as it tries to grow even more?
That's a good point. One of the most significant challenges is just how sensitive these systems are to their environment, particularly temperature changes and mechanical vibrations.
Okay, temperature. How can a small temperature shift really affect things at the nanoscale? Seems minor.
It's actually a fundamental physics problem down there. At the nanoscale, even a tiny temperature increase, maybe just 1 degree Celsius, can cause components to expand or contract by, well, a few nanometers.
Which sounds tiny, but
But it's enough.
yeah.
It's enough to throw off the incredibly delicate alignment you need for, say, semiconductor lithography.
Yeah.
It could potentially ruin an entire microchip.
Wow.
So companies are pouring resources into things like thermal compensation systems, using advanced materials that don't expand much. But these solutions, they add complexity and they add cost.
Right. And vibrations. I'm guessing my shaky desk isn't the place for one of these.
Definitely not. Mechanical vibrations are another huge challenge, especially for those ultra-high precision uses like advanced microscopy. Even tiny disturbances like a truck driving by outside, or even the building's air conditioning system can compromise the results. It can distort alignments, create noise in sensitive instruments.
So it's a constant battle to keep things perfectly still.
It really is a battle against the physical world at that scale. And while there's lots of research into vibration resistance stages, isolation systems, again, these solutions can be quite costly and add more engineering complexity.
Speaking of cost, that sounds like it could be another major barrier.
Precisely. That's the other big challenge, the high upfront cost of these systems. The precision is invaluable for certain applications, sure, But the price tag can definitely be a barrier, particularly for, say, smaller businesses or university labs, maybe startups in R&D or biotech.
So there's a need for cheaper options.
There really is. As the market grows, there's an increasing need for more cost-effective solutions that can still deliver that high precision without, breaking the bank. Developing more affordable components, better materials, maybe improving manufacturing techniques that will be crucial to make these systems more accessible.
Okay, so despite those challenges, environment, cost, what exciting developments can we expect looking ahead? What does the nano future hold for these systems?
Well, looking forward, the market really seems poised for some significant advancements. There's a big focus now on automation, miniaturization, and also integration with other technologies.
Miniaturization makes sense. Smaller is often better.
Exactly. We're seeing a clear trend towards smaller, more compact, lighter systems. That's going to make this kind of tech much more accessible, easier to integrate into machines in semiconductor manufacturing, aerospace, biotech.
And you mentioned integration with other tech, like AI.
Yes, absolutely. The integration of AI and machine learning algorithms, that's going to be transformative.
Yeah.
Imagine systems that can optimize their own positioning in real time.
How would that work?
It means they could make dynamic adjustments to accuracy on the fly, minimizing the need for human intervention, making operations much more efficient. Really crucial for industries that need fast and super precise positioning.
Interesting. What else?
Advances in material science will also be huge, leading to more robust components, maybe more temperature-resistant ones, so the systems can work reliably even in tougher conditions. And of course, just ongoing nanotechnology innovations themselves will keep unlocking new applications, especially in fields like quantum computing, nanomanufacturing, and potentially groundbreaking high-precision medical devices too.
It really sounds like a convergence of different advancements, all boosting nano positioning. And this drive for ultimate precision, it's not just in these core industries, is it? It feels like a broader trend.
It absolutely is a broader trend. Take something seemingly different, that groundbreaking 2D, 3D cinema screen Harkness screens launched back in September 2024, the one designed for laser projection.
Yeah, I remember hearing about that. Better brightness, better 3D.
Exactly. But think about how they achieve that. That pursuit of ultimate image quality requires incredibly precise alignment of those lasers to hit every single pixel perfectly.
Ah, I see the connection.
While it might seem unrelated, the underlying control systems for those lasers often rely on components demanding nanometer-scale precision. It just shows how deeply this demand for ultra-precise control is weaving its way into all sorts of technological frontiers.
What an incredible deep dive into a world working at scales that are, frankly, hard to imagine. We've seen how these nano-positioning systems, these super precise devices, are just fundamental for controlling things at the nanometer level.
Right.
They're driving really substantial market growth, projected to hit, what was it, USD 463.5 million by 2032. All pushed by this insatiable need for precision everywhere from chip making to medical diagnostics.
That's right.
And we explored the competitive side too, how companies are pushing innovation and precision, yes, but also speed, durability. And we tackled the big challenges like sensitivity to environment and the high costs and how research is trying to address those.
It's a dynamic field.
It really is. It's just clear these systems are becoming integral across so many critical industries, biotech, aerospace, optics, you name it.
Thinking about this pervasive need for nanometer precision
Yeah.
and how it's embedding itself into everything from quantum computers to new manufacturing methods, it does raise an interesting question, doesn't it?
What's that?
Well, if the very fabric of our engineered world is increasingly built with this kind of absolute control right down at the atomic level, how might that redefine what we even think is possible in terms of creating entirely new materials, maybe? Or even, I don't know, shaping the environment around us in new ways?
That is a thought-provoking question to leave everyone with, something to really mull over the immense potential unfolding at the nanoscale. Thank you for joining us on this journey into the ultra-precise world of nano-positioning systems.
My pleasure.
We hope you continue to reflect on these fascinating technologies and keep exploring their really profound potential.